Hello, everyone. I want to thank you for joining me on this journey through cloud computing concepts. This is the first part of the Cloud Computing Concepts course, which is a two-part course. This course here is about the internals of cloud computing. This means that we'll go underneath the hood and look at the distributed systems concepts and the distributed algorithms and the distributed techniques that underlie today's cloud computing technologies. This course is not about how to write cloud systems or cloud applications. There is a separate course that's coming up called Cloud Applications. And this course is not about networking either in the cloud. There's a separate course called Cloud Networking that's coming up that's about networking inside the cloud. All of these courses, the Cloud Computing Concepts course, this course, both the parts, as well as the Cloud Applications course and the Cloud Networking course are part of a cloud specialization, which is being offered to students. What we'll discuss in this Cloud Computing Concepts course, both Part 1 and Part 2, is three things. Concepts that underlie today's cloud computing systems, especially distributed systems concepts, techniques that are used fairly widely in a variety of cloud computing systems today. And we'll also, while discussing concepts and techniques, look at some facets and some aspects of industry systems, including open source systems like Hadoop, NoSQL storage systems, and many others. So the Cloud Computing Concepts course is really a mix of distributed systems with a mix of distributed algorithms, and both of these combined as applied to cloud computing systems as they are today. So what we'll discuss in this first part, the first 5-week part of the Cloud Computing Concepts course, first we'll have an introduction to clouds, what they are, why they are the way they are. We look at MapReduce and key value stores, two of the emerging sub-areas of cloud computing. Then we look at some of the precursors, previous generations of cloud computing systems like peer-to-peer systems and grids that are ancestors, parents of today's cloud computing systems. Then we'll go underneath the hood and start to look at widely used algorithms for gossip, membership, Paxos for consensus, and also classical algorithms including time and ordering, snapshots, and multicast. Along the way, in some weeks, we'll have interviews with leading managers and researchers from industry as well as academia, and I hope these will be interesting to you as well. The course is structured so that you can learn as you move along. So there are 5 homeworks spread throughout the course, as well as a programming assignment. The programming assignment involves writing code inside an emulator. In the first part of C3 course, you will be writing a membership protocol inside an emulator that we'll provide to you. We'll provide you the template, the C++ template, and you can write it, and the one final exam. Well, cloud computing is an exciting area to be studying, to be working in, and it is also a very dynamic and continuously changing area, and that's part of what makes it exciting as well. I'm really looking forward to working with you and interacting with you as this course moves along. Come join me as we start our tour of the cloud computing concepts landscape. Welcome to this Cloud Computing Concepts course. In this lecture, we'll be covering several concepts that are assumed as a part of the topics that we'll be discussing in the Cloud Computing Concepts course. So we'll be covering several of the basics that are considered to be basics in computer science. Typically, some of these concepts are concepts that computer science students learn in their first couple of years. So basic data structures, we'll discuss two different data structures. The first one is a queue. A queue is essentially a first in, first out data structure. Elements of the queue could be any data types. In this example here, I have elements that are integers. So in this example right now, the queue has 5 elements, 3, 5, 8, 0, 7. This is an ordered list of elements. When you remove an element from the queue, you remove it from the head of the queue. In this case, the head is the element 3. When you insert a new element, you insert it at the tail of the queue, which means that if I insert a new element, say 1, it's going to get inserted right after 7 in this queue. So removal always comes from the head, while insertion always happens at the tail. So for instance, given this particular queue consisting of 5 elements, if you dequeue or remove an item, then that item will be 3. At that point of time, the queue will only consist of 5, 8, 0, and 7, with the head pointing to 5. The next item that you dequeue or remove will be 5. Okay? After that, the queue will consist of only 8, 0, and 7. Then the next item that you dequeue will be 8, and so on and so forth. Dequeues or removals as well as insertions can occur concurrently, so you can remove an element, but at the same time also insert an element at the tail. So that's a queue, which is a first in, first out data structure. A different data structure is the stack, which is a first in, last out data structure. Imagine a stack of dishes that you place on your table. The dish that you put at the top, that you add the last, will be the first one that you can remove, right? And that's essentially a stack. So remove, or also known as a pop, happens from the top, and insert or push also happens at the top. So in this case, if you push a new element into this particular stack, say 9, the 9 will go above 3. After that, if you pop or remove an element, that's going to be the last element that you added, which is 9 in this case. The next pop after that will get 3 because 9 was just removed, and 3 is now the top of the stack. After you remove 3, the next pop or removal will get you 5, and so on and so forth. After that, you get 8, and then 0, and 7. So once again, the removal always returns you the last item that was added, and insertion or push adds an item right to the top of the stack. So these two data structures, queue and stack, are used very widely in computer science, and in fact, we'll be using the notion of a stack right away when we discuss processes soon in this particular orientation lecture itself. What is a process? A process is essentially a program in action. For instance, you might write a program in a language like C, C++, Java, or Python, or Ruby on Rails, whatever it is, doesn't matter what the language is. And when you execute that program, say from the command line or from a GUI, that executing program is called a process. For instance, here I have a C-like program which has a function main, which in turn calls a method f1, which in turn calls the method f2. This is shown pictorially here, main calling f1, calling f2. When you instantiate this program and execute it, it becomes a process, which here in this case is labeled as p1. So this code part shown here is only the program itself. The process itself consists of multiple other components. The code typically doesn't change, but the other components might change. What are these other components? Let's look at them one by one. First of all, there's a program counter, which is an index into the code which says where the program is right now. What is the exact line number within the code where the program is executing right now? Next, you have a stack, which is used by the functions to pass arguments and return values. For instance, when main function calls f1, any arguments that it needs to pass to f1 are passed via the stack by pushing an element on top of the stack. F1 can then pop that element off and obtain the arguments that are passed to it. Similarly, when f1 calls f2, it then pushes on top of the stack the arguments that it has for f2, and f2 can retrieve these arguments by popping on top of the stack. When f2 is done, it can return the return values to f1 also by pushing the return values on top of the stack, so that when f1 resumes, it can pop the top of the stack to obtain the return values from f2. Similarly, f1 returns its return values to main by pushing on top of the stack. Now, the functions themselves might declare variables. Some variables might be local variables, and local variables are also typically maintained on top of the stack. I'm not showing them here, and this is the reason why when a function or method is completed in its execution, any local variables declared inside are then gone, because that part of the stack has been popped. In addition, functions might also create new memory by, for instance, calling malloc or new. In this case, I'm showing such a variable x, and such variables are stored in a separate data structure associated with the process known as the heap. Also associated with the heap are also registers, which typically refer to the recently accessed variables in the process itself. So, for instance, this variable x is present in the heap. Such malloc or new variables also need to be explicitly freed in most cases. However, some programming languages have automatic garbage collection. Now, the reason we're discussing the process here is really the main reason is that when we talk of distributed systems, we're going to talk of multiple processes communicating with each other, and we mostly focus on process-to-process communication, although later on we'll also talk about how procedure calls or function calls can cross process boundaries. In addition, the other reason we're discussing the process here is that when you take a snapshot of a process, when I say a process takes its own snapshot, this essentially includes everything that I'm showing here on the slide and maybe a few more elements. It includes the code, the program counter, the current status of the stack, the current status of the heap and the registers, and then a few other elements. Essentially, this information is enough to resume this process from here onwards. Okay, speaking of computer architecture, let's discuss a simplified version of computer architecture. Computer architectures today can be very complicated, but typically when we think of how a process executes in a computer architecture, we can think of a simplified view. So there's a CPU which executes the actual instructions which are present in your code. There are also a bunch of registers that are co-located with the CPU. These are small pieces of memory that can be accessed very quickly by the CPU. Typically, there's only a small number of registers, typically not more than a few tens of registers. There's also cache, which is a slightly larger memory than the collection of registers, and the larger piece of memory is the slower it is to access it. So accessing a cache is slower than registers, than accessing registers, but accessing a cache is still pretty fast. Then beyond the cache, there is the main memory, or the random access memory, or the RAM, which is even larger than the cache, and the memory itself, therefore, is slower than the cache, but still it's pretty fast. And then finally, there's hard disk, or if you like a solid state drive, a flash drive, or whatever, which is a lot more memory than the main memory, but of course it's much slower. So as you go up from disk to memory to cache to registers, the speed increases, the total amount of storage space that you have decreases. So when you write a program, such as C++ or Java or C, and you compile it, it gets compiled to low-level machine instructions. These machine instructions might be specific to the architecture of the machine on which you're running, or it might be a virtual machine, like a JVM kind of code. In any case, these low-level machine instructions are the executable version of your program, and this is stored in file system on your disk. When your program starts executing, when it becomes a process, the CPU loads instructions in batches, or in a more simplified way, it loads instructions one by one. It loads them into memory and then into cache and into registers. Typically, the cache and the registers contain the last few accessed instructions, so they follow what is known as the least recently used principle. Now, as it executes each instruction, the CPU, which is executing the process, loads the data that is necessary for the instruction into the memory, and then it's necessary into the cache and the registers. And if there are any necessary changes that happen to a variable like x, then these are stored into a memory, first into cache and then into memory. Once in a while, you may need to store something on disk so that you have a permanent storage. So in case the process goes offline, then you still have some data saved. For instance, the program might open a file and write something into the file. So in this case, you may want to write those updates to the file onto the disk. Now, of course, this is a very highly simplified picture. Computer architectures can be far more complex than this today, but for our practical purposes in this course and as far as explaining how processes work, this will suffice. So next we move on to a few mathematical topics. The first mathematical topic is a big O notation. Now, big O notation is one of the most basic ways of analyzing algorithms. When I give you an algorithm and I say analyze the algorithm mathematically, essentially I expect you to come up with at least a big O notation and an analysis of that algorithm. The big O notation describes an upper bound, the behavior of an algorithm, as some variable is scaled or increased in value all the way to infinity. Typically, this variable is the size of the input, maybe the number of input elements. You'll see a few examples of this. So essentially, this big O analysis tells us how does the algorithm itself scale as the size of the input is increased. This analyzes the runtime or typically another performance metric as well. Most of the time we analyze runtime. Sometimes, as you'll see in the course, we analyze things like number of messages, even bandwidth that is exchanged in the total network itself. The important thing about big O notation is that it captures worst case performance. Okay, so this is not expected performance or best case performance. Big O is worst case performance. Given this algorithm, what is the worst that it can do in terms of this performance metric that we're measuring? So essentially, when I say an algorithm A is order of foo, this means that algorithm A takes less than c times foo time to complete, assuming time is the metric we're measuring, for some constant c, a fixed constant c, beyond some input size n. Okay? Typically, this foo that is present in the definition is some function of the input size n. For instance, I could say that an algorithm is order n, which means that algorithm A takes less than c times n time to complete for some constant c beyond some input size n. Similarly, algorithm might be order n squared, which means that it is quadratic in time and it takes time less than c times n squared for some constant c. Once again, when we say order n square or order n, notice that we do not include the constant c in the definition itself. This is because the constant is irrelevant. As long as there is a fixed constant, some fixed constant, that is good enough for us as far as big O notation is concerned. Okay, so we do not state the constants in big O notation. So let's see a couple of examples. So first, I give you an unsorted list of, say, integers, and I ask you to search for a specific element in the list. This essentially means that you have to iterate through the list, one item at a time, and search for the element by trying to match it with each element already present in the list. What is the worst case performance? That's what we need for big O notation, right? So the worst case performance happens when either the element is not there at all in the list, so you return a false, or the element is the very last one in the list, the very last one that you match against. Therefore, the worst case performance involves n operations, and the number of operations involved is less than c times n, where c equals 2, because the number of operations is n, where n is the size of the list. Okay, so the time as well as the number of operations, assuming each operation takes 1 unit of time, both the time taken for this algorithm, which iterates through the list, as well as the number of operations, are both order n. That's why we say order n over here. Let's take a different example to see how big O notation works. This deals with insertion sorting of an unsorted list. So suppose I give you a list of elements, say integers, and this is unsorted, and I ask you to sort them, say, in increasing order of the elements. The insertion sort algorithm works as follows. First, you create a new list that is empty. Then you iterate through the elements in the unsorted original list. You remove one element at a time, and you insert that element in the new list at the appropriate position. Essentially, you sort through the new list linearly, searching for the right position where this element should be. So if you do this, the first element, of course, takes one operation to insert. That's one insert operation. The second element, in the worst case, takes two operations to insert. One operation for the comparison with the one element that's already present in the new sorted list, and one more operation to insert. Imagine the worst case where this second element is inserted right at the very end of the list. Similarly, the third element will take three operations to insert, where the first two elements compare it with the two already existing elements, and the third operation inserts it at the very end of the list. If you go on like this, then the ith element takes I operations to insert, and you can calculate that the total time required to insert all the elements is 1 plus 2 plus 3, so on till n, and this is a well-known sum which comes to n times n plus 1 divided by 2, which is less than 1 times n squared. So with the value of c equals 1, this insertion sorting example is an algorithm that takes order n squared in time and also order n squared in number of operations. Next, we'll look at a little bit of basic probability. Before probability, we need to discuss a few definitions. The first definition is a set. A set is essentially a collection of things. So for instance, a set S might be a set of all humans who live in this world at this current moment. A subset is another set, which is a collection of things that is a part of the larger set. So I might describe a set S2, which says a set of all humans who live currently in Europe today. S2 is a subset of S because every element that is present in S2 is also present in S, but the reverse is not necessarily true. Okay, so now probability. Any event has a probability of happening. Okay, so let me give you an example. If you wake up at a random hour of the day, say you just wake up at some random hour of the day, say you're jet lagged or something, and I ask you what is the probability that the event at the time is between 10 a.m. and 11 a.m. Let's try to calculate this. Well, there are 24 hours in a day, so you have a set that consists of 24 elements, one for each hour, 12 a.m., 1 a.m., 2 a.m., all the way to 10 a.m., 11 a.m., 11 p.m. So when I say an element like 1 a.m., I mean the hour between 1 a.m. and 1:59 a.m. Similarly, 10 a.m. means 10 a.m. and 10:59 a.m. Out of the set of 24 elements, you pick one at random, and the probability that you're going to pick 10 a.m. is essentially 1 divided by 24, because you're picking one element at random, and there are 24 elements in the set, and the probability that you pick that one special element 10 a.m. is 1 over 24, because you want to be lucky of that to pick that 10. Okay, so the probability that if you wake up at a random hour of the day, the time is between 10 a.m. and 11 a.m., that probability is 1 over 24. Now, there are multiple events, so you might need to calculate the probability of conjunctions or disjunctions of these events. I'll describe what these are soon. So say E1 is one event, and E2 is another event, and E1 and E2 are independent of each other. This means that E1 does not influence E2, E2 does not influence E1. Then the probability that E1 and E2 both happen is essentially the multiplication of these probabilities. So you take the probability of E1 multiplied by the probability of E2, and that gives you the probability that both E1 and E2 are true. Let's discuss an example of this. Suppose you have three shirts. They're colored blue, green, and red. And also you wake up at a random hour and blindly pick a shirt. You put your hand into your closet and you blindly pick out a shirt. What is the probability that you woke up between 10 a.m. and 11 a.m. and that you picked a green shirt to wear? Well, the first probability of the first event, that you woke up between 10 and 11, is essentially 1 over 24, like we calculated on the previous slide. The probability that you pick the green shirt is essentially 1 out of 3, because there are 3 colors of shirts. You have 3 shirts, and you want to pick the green one. You want to be lucky to pick the green one, so that's 1 over 3. And so the probability that both these events are true, that you woke up between 10 and 11, and that you wore the green shirt, is the multiplication of the probabilities of those events. So it's 1 over 24 times 1 over 3, and that gives you 1 over 72. One of the things that you have to be careful about here is that if E1 and E2 are not independent, meaning that they influence each other in some way, then you cannot multiply the probabilities with each other. Okay, so for instance, if the shirts that you have in your closet change from 1 hour to another because, say, someone in your house changes them around, then you can't necessarily multiply these probabilities as they are here. A different thing that we need to do with two event probabilities is to OR them. So if I give you two events E1 and E2, and I ask you the probability that of either E1 or E2 happening, then you can say that the probability of E1 or E2 is the probability of E1 plus the probability of E2 minus the probability of E1 and E2. Okay, so this is the intersection probability here. If you do not know probability of E1 and E2, this last term over here, then you can write the inequality probability of E1 or E2 is less than or equal to the sum of the constituent probabilities. Okay. Sometimes we use these inequalities to upper bound the probabilities of the disjunctions, as we see here. The DNS refers to the domain name system. It's essentially a name resolution system. It is run as a collection of servers throughout the world, and it helps you to translate URLs, actually domain names, into IP addresses. So the input of the DNS is a domain name, such as Coursera.org, and this is a human-readable string that uniquely identifies the object. So we humans can easily remember a name like Coursera.org. Actually, we really remember URLs like class.coursera.org/foo, and when you enter this into your browser extracts the domain name from this URL and then sends this off as a query to the DNS system. The DNS system that returns to you the IP address of a web server that potentially hosts that content, and the IP address is essentially a target or an address or an ID, and it is a unique string that points to the object. The difference between an ID and a name, the output and the input to a name resolution system like DNS, is essentially that IDs are harder to remember. It's harder for us humans to remember IP addresses. It's much easier for us to remember names. Also, IP addresses change, but names don't. Now, the IP addresses might refer to an actual web server, a unique web server that actually hosts the content, so that now your client browser can send a TCP and HTTP request to that server, or it might refer to an indirect server or even a group of servers, such as a content distribution network, such as from Akamai. The funny thing about name resolution systems is that they can be changed. So the ID or the address obtained from one name resolution system can be given as a name to another name resolution system, and that can return a different address, and so on and so forth. And you can keep doing this until you reach your final object itself. Graphs. So when we say graphs in computer science, we don't necessarily mean plots which have x and y axes. A graph is essentially a network. So here I'm showing you a graph of some cities, Amsterdam, Boston, Chicago, Delhi, and Edmonton, and the travel times between those cities by air, rounded up to the nearest hour. Okay, so traveling from Amsterdam to Boston takes about 6 hours, traveling from Chicago to Delhi takes about 14 hours. Say these are the flights that are available on some particular airline. Right? So you see both cities here, as well as connections between pairs of cities, and also some values along those connections, which are the number of hours that it takes to transit between those cities. These all have names in terms in the world of graphs. So each city would be a node or a vertex. Each connection between a pair of nodes would be called an edge, and the value along an edge is called the edge weight. Also, when I say that A is adjacent to B, this means that A has an edge that connects it to B directly. Typically, an edge only goes between two nodes or two vertices. An edge does not cross three nodes. So here, for instance, I have 1, 2, 3, 4, 5 vertices. And how many edges do I have? I have an AE edge, an AB edge, a BE edge, a BC edge, and a CD edge. So I also have 5 back to this as a reference whenever you need it throughout the course.
like Earth created, the universe was created. No, before humans, the universe was created. Like, hmm no,
So welcome to the Linux Foundation's Introduction to Open Source Software Development, Linux and Git Specialization. My name is Jerry Cooperstein, and I am the Training Program Director at the Linux Foundation. I won't say much about myself other than to say that I'm by training a theoretical nuclear physicist. I've worked with computers as far back as the 1960s, and I helped set up the training program at the Linux Foundation back in 2009. Today, we have grown to a rather large program with a large catalog of courses, both of the instructor-led variety, virtual courses over the internet as well as many e-learning courses. The Linux Foundation itself is a nonprofit organization. It was founded in 2000 and is the home of Linux creator Linus Torvalds. Ever since then, it has provided a neutral environment where Linux kernel development could be protected and accelerated. Linux's success catalyzed the growth of the open source community and demonstrated the commercial efficacy of open source. It inspired countless new projects across all industries and levels of the world's technology infrastructure. Today, the Linux Foundation's work extends far beyond Linux, fostering innovation at every technology layer. We partner with the world's leading developers and companies to solve the most challenging technology problems and accelerate open technology development and commercial adoption. Our mission is to provide experience and expertise to any initiative working to solve complex problems through open source collaboration, supplying the tools to scale open source projects. This includes bolstering security, best practices, governance, operations, and ecosystem development, and training such as this course. By doing so, the Linux Foundation has become the umbrella organization for many critical open source projects that power corporations across all industry sectors. The Introduction to Open Source Software Development, Linux, and Git Specialization was created to provide you with a strong foundation for working comfortably and productively in open source development communities, a better understanding of the Linux environment as well as methods and tools required to successfully use it, and supply training on using Git, the distributed version control system. This specialization is aimed at computer users and developers already possessing experience with another operating system, but who have a more limited knowledge of working in a Linux environment, as well as at Linux users seeking to gain a good working grasp of Git. The specialization has been divided into 4 courses. The first is Open Source Software Development Methods. The second is Linux for Developers, the third is Linux Tools for Developers, and the fourth is Using Git for Distributed Development. Each course uses several methods to present and solidify the learning material, including videos, readings, examples, external resources, lab exercises, graded and ungraded assessments and discussions, etc. To complete the specialization and to earn your specialization certificate, you will need to finish all 4 courses, obtain a course certificate for each course in the specialization, and pay for the specialization. Please note there is no, quote, capstone project. Instead, your newly acquired knowledge and skills will be assessed based on the graded assignments you submit in each course. It's required that you pass all of the graded assignments to successfully complete the individual courses, as well as the entire specialization. To learn more about Coursera specialization requirements, please click on the link provided below this video in the download section. We are excited to have you in this class, and we look forward to your contributions to the learning community. Thank you.
So another thing that I'm going to talk about for class diagram is what we call association. So notice when the participation is going to be mandatory. Don't replace every single hash
I'm John Mafrano, Senior Technical Staff Member and DevOps Champion at IBM Research, and I'd like to welcome you to Introduction to DevOps. This course will help you understand the cultural as well as technological transformation that is required to not only make your DevOps initiative successful, but allow it to flourish. According to a recent DevOps Institute report, demand for DevOps skills are expected to grow 122% over the next 5 years, making it one of the fastest growing skills in the workforce. Unfortunately, having skills alone won't ensure success. Gartner predicts that through 2022, 75% of DevOps initiatives will fail to meet expectations due to issues around organizational learning and change. I can't stress enough, the number one reason failing to meet expectations is not around skills, it's not around tools, but due to issues around organizational learning and cultural change. Cultural change can have a significant positive effect on DevOps success. According to George Spafford, Senior Director Analyst at Gartner, people-related factors tend to be the greatest challenge, not technology. You see, DevOps is not a tool. DevOps is not a job title. DevOps is the practice of development and operations engineers working together through the entire software development lifecycle, following lean and agile principles that allow them to deliver software in a rapid and continuous manner. If you want to do it fast, you want to do it continuously, you need to adopt the shared mindset that is at the heart of the DevOps culture. So, how do you change a culture? In order to change your culture, you need to learn new ways of how to think, how to work, how to organize, and how to measure. Throughout this course, we'll look at how businesses are being affected by disruption and how a DevOps culture can help. We'll cover thinking differently through social coding and improving software reuse and sharing. We'll learn about ideas from lean manufacturing, such as working in small batches to reduce waste, creating minimum viable products to gain valuable insight. We'll explore working differently by using test-driven and behavior-driven development techniques to ensure repeatable behavior and high code quality. You'll see how adopting continuous integration and continuous delivery practices ensure that every change contributes to a potentially shippable feature. But tools are not the solution to a cultural problem. According to the 2021 Accelerate State of DevOps report by the DevOps Research and Assessment DORA team, which, by the way, represents 7 years of research and data from more than 32,000 professionals worldwide. Team culture makes a large difference to a team's ability to deliver software and meet or exceed their organizational goals. In order to change your culture, you'll need to organize your teams differently, because how you organize directly impacts the architecture and design of the products that you produce. You know, humans have a knack for figuring out what behavior is rewarded and then doing, or at least pretending to do, that rewarded behavior. For the last cultural change we'll discuss is measuring differently, and how changing your measurement system to encourage the correct behavior is critical for your success, because you get what you measure. We'll also look at how to avoid being fooled by vanity metrics and how you can use actionable metrics to gain valuable insight about your product and your customers. Implementing a DevOps initiative isn't easy, but it can be very, very rewarding. In order to really embrace the DevOps culture, you have to be willing to make changes. Lots of changes. You must be willing to experiment and understand that it's okay if an experiment fails, because every failure is a learning opportunity. So fail fast. You need to foster the core values of teamwork, accountability, and trust. So join me in exploring how you can transform the culture and technology of your organization so that your DevOps journey will be a successful one. Watch the videos, take the quizzes, and interact with your peers on the forums, because DevOps is a team sport and collaboration is encouraged. I like to say, we don't do DevOps, we become DevOps.